Hello, everyone. Welcome to the Supercomputing Spotlights webinar series. This features short presentation that highlights the impact and successes of high-performance computing throughout the world. Our main objective in our activity group on supercomputing at SIAM is to perform or do outreach, promote HPC, engage with the younger generation, and inspire. Everyone is welcome to join those events. We do post our recording on our YouTube channel. Those are our main initiative in our activity group. We want to promote HPC via the social media. We also have webinars to further inspire our community, and we also have inclusivity activities mostly on social media, but also on few venues where we are able to do so. We have a new website. It has more and more content. We usually upload information related to HPC and our webinars, as well as activities and research around HPC. I'd like to have one slide on SIAM Parallel Processing 24 next year conference for scientific computing in Baltimore, Maryland, in the US. We still have time to register. The deadline for pre-registration is February 5. Please do join us for this important meeting. So today, our speaker is Laura Schulz. So this is a panel-style webinar. Laura will be our moderator. So the topic will be about quantum computing and quantum accelerated HPC. So we'll have a panel discussion, and we have 4 esteemed speakers joining us today to discuss this topic. So Laura is currently the department head of quantum computing and technologies at the Leibniz Supercomputing Center in Garching, Germany, where she drives multiple efforts toward integrating emerging quantum accelerators into several layers of the high-performance computing ecosystem. Laura is the PI for Germany EuroQXA project to sit Euro-HPC joint undertaking quantum system in Bavaria, and manages a robust portfolio of funded projects and a great team to achieve LRZ quantum strategy. Before joining LRZ, she was part of the Computation Directorate at Lawrence Livermore National Laboratory, as well as LNL's High Performance Computing Innovation Center. Recently, Laura was named an HPC Wire 2023 person to watch. Without further delay, Laura, I'll let you take it from there.
Great. Thank you, Hatem. So hello, everyone. So as Hatem mentioned, I am coming to you today from Leibniz Supercomputing Center near Munich in southern Germany. This has obviously been a very eventful week for us. As you may have seen in the news, southern Germany has been inundated with just a sheer volume and tempo of snowfall that we haven't seen before. Some of us are still digging ourselves out of it. But this week is also eventful. Today is also an eventful day because here in Germany and several other countries around us, it is St. Nicolaus Day. So this is a holiday that stems from the tradition of children putting their shoes and stockings outside at nighttime, only to wake up in the morning to find them filled with treats given by a figure known as St. Nicolaus, which over time has merged and morphed into a figure known as Santa Claus in several parts of the world. But St. Nicolaus here at LRZ did not fill our shoes with treats, but this year he really one-upped his game, because currently and literally as we're speaking, as we're taping this right now, he has had his favorite contracted transporting company deliver a brand new ion trap quantum computer to our quantum integration center here at LRZ. So this is an AQT system. We'll learn a little bit more about that. The press release just went out yesterday. We're very excited to add this to the portfolio of quantum systems that we already have at LRZ in the superconducting line. And we have several on the way coming and pending for the future. And that kind of brings us to our topic today, and that's really about quantum computing and HPC. So supercomputing centers like LRZ and HPC users worldwide, we're all really starting to explore this new form of computing potential. We're trying to understand how its unique computational behavior could be applied to achieving solutions, scientific solutions better, faster, greater resolution, greater complexity, what role it can actually play as an added accelerator capability within the whole HPC ecosystem. So this is all new territory for pretty much all of us in the HPC community, and that's really what kind of inspired the idea for this webinar today. And, you know, speaking with Hatem, there's so much new information, new ideas to share, new things to learn. And so what we wanted to do was to bring you this webinar and to really kind of under this theme of everything you've ever wanted to know about quantum computers and quantum HPC, and we're most certainly not afraid to ask. So that's kind of the premise of this, and we're going to pitch a bunch of questions to our panelists today. And with that, I want to introduce 4 really great folks that we have joining us today. First, I'll just go down the line. Bruno Takatani, he's coming to us today from IQM Quantum Computers. There he is a project manager developing on the integration of the company's quantum computers into the HPC environment. So he's really sitting square in this topic. And with him is Thomas Mons. He is the co-founder of Alpine Quantum Technologies, and this is ion trap-based technology. We also have Chima Boaza, excuse me, I practiced that. She is the regional manager for the Middle East for Pascal, which is neutral atom based. And then adding a little bit of sparkle to the group with diamond-based quantum technology, we have Mark Mattingly-Scott. So Mark is the Chief Revenue Officer and the General Manager for EMEA for Quantum Brilliance that stemmed out of Australia. And I know that they've got presence here in Germany as well. So to kind of kick this off, what we're going to do, I'm going to ask each of our speakers to just spend about 5 minutes or so introducing themselves, the company, their technology, giving us a little bit of a baseline that we can start off for our discussion. And then from there, we will just have a friendly, chatty conversation, throw some questions around, try to anticipate some of the things that you might be thinking about coming from the HPC space. What would be questions that you would be interested in exploring? I have a team here at LRZ of about 30 folks, and when I was asking them, many of them came from the HPC space and came new into this hybrid interdisciplinary space of HPC quantum, and I asked them a few questions about what were some of the early questions that they had. So I'm going to pitch some of those around to this group as well, and so we will see what we can discover and what sort of interesting conversation that we can have in this next hour. So with that, I'm going to go ahead and ask Bruno to start. So Bruno, we'll need to, if you would like to use slides, we will need you to have you share your screen.
All right. Done working?
Yep, there you go.
Perfect. All right. Thanks, Laura, for the introduction. Thanks for the invitation to be here. I guess thank you for you watching us online as well for the interest in quantum computing. I'm going to have to say thanks, Laura, for giving us 5 minutes to talk about a bunch of stuff. So I'm probably going to rush a lot. Let's see how I go. So starting with introductions again, hi, I'm Bruno. Well, my background is in quantum physics, quantum computing. I have worked on several different topics on it. And for the last 2 years, I've been at IQM Quantum Computers as currently product manager. Now, what we do at IQM is we build quantum computers. And we build quantum computers based on superconducting technology, as Laura said, which are those pictures that you typically see online when you see anything about quantum computers. Now, we build quantum computers, and that is an extremely challenging. Oops, okay, that shouldn't have gone that fast. I am not done yet. Okay, that's not working. Sorry for that. Yeah. So again, as I said, we build quantum computers, and that is an extremely challenging task. As such, we need a large group of people doing that. So at IQM, we have at this point close to 300 people of very specialized skills in those people, a very diverse crowd And we also need a lot of funding, and we're happy to have secured that kind of funding to date. And we have put those to very good use in developing several things, including a very ambitious project we had of building our own private foundry where we can actually manufacture our systems. It's really cool. I was blown away when I visited the place. And that is very important for us to speed our R&D cycle. And in doing so, we have also been able to get a very cohesive organization. And from that, we are very proud to have sold also 2 systems already, 2 full quantum computers, one in Finland and another one to LSE in Germany. Now, oh my God, I don't know what's going on here. So it's probably going to happen again. As a quantum computing company, we are what's called a full stack quantum computing company, which means our activities really expanded the whole spectrum in quantum computing, starting off with designing of our chips, manufacturing in the foundry that I have just mentioned, testing them, and that is a very critical point, and we're very happy to be able to claim to have best-in-class performance for our systems. And then we have to package that all into a fully integrated system, which includes specializations so that we can integrate it and deploy it to HPC centers directly. So as an example, having a rack layout for the system. But for us to actually span the whole spectrum, that means we also have a team working on algorithms and applications and really trying to push our systems to the limit. The ones that we have now and the ones that we build in the future. Again, that same problem. So I wanted to go very quickly through the technology so you can understand. As I said, we have, our technology is based on subconducting qubits. So for those subconducting circuits for the elements of that to actually behave as the qubit must, they need to be very cold. So this is an open fridge, like the ones that you typically see. The quantum processing unit, the QPU, sits here in the bottom, and that needs to be at milli-Kelvin temperature. So we leave room temperature outside here, 300 Kelvin, all the way down to milli-Kelvin, tens of milli-Kelvins. So what's happening at each of those steps is that you're decreasing the temperature so that you can finally reach that desired temperature. And this is, just the schematics. I'm not going to go through anything. There's a lot written here, but just schematics to show you how that temperature decrease happens. And the QPU sits here at the bottom. And that QPU looks like, you can see some renderings here. And we have gone through 5 qubit systems to 20. We're now at the testing phase for 50 4 qubit systems and already working towards larger systems. And you can see here the circles representing qubits, and this orange element here in the middle is responsible for coupling different qubits. Now, what we do with all of that is we have now a set of products that we can offer, starting off with IQM Spark. That's an affordable system based on 5 qubits, and that is actually tailored to be deployed and used by research and education institutions. Then our flagship system, which we call IQM Radiance, has our best-in-class QPUs inside, and it's tailored to be deployed to HPC centers. And we also have services such as training and consulting. So with that, I hope to have given you an idea of IQM efforts in this, in what we're doing. And I thank you for your attention.
Great. Thank you so much, Bruno. So clipping right along to get through all the folks and then opening up for questions and conversation is our next speaker. So this is Thomas Mons. And, you know, I mentioned about St. Nicolaus and Santa Claus at the beginning. So in these Germanic history or legend of St. Nicolaus. So he had a companion that came around with him. This was the Krampus. And so basically St. Nicolaus was the good guy who gives out the sweets and the candy. And for the children who are not so good, the Krampus would throw you in a burlap sack and drag you off. So with that in mind, Thomas Mons, would you like to give us an overview of AQT?
So when I was younger, I got more Krampus than Nikolaus. That's the way it is. So a quick overview about what we do in Innsbruck, in the south from Laura. And like just a quick side comment is like we see how much snow you have, and we have no clue why you have traffic jams, because for our standards it's like that's an afternoon snow. But yeah, so our background along those lines of being used to those things, we are working on quantum technologies. We've been working on quantum in general for a long time. So that's for us similar to the snow, like quantum is in our blood and has been in our blood for the last 2 decades. So the founders, including Peter Zoller and Rainer Blatt, have been working in this field since 1995, proposed how to control individual atoms and shine lasers on them, similar to what likely Pascal will show you after me, and had some ideas on how can we release gates, how can we build a computer out of that. Zoller had the first ideas in 1995 together with Ignatius Rack, who is now a director at Max Planck Institute in Munich. But yeah, there's one thing is the theory, one thing is the implementation. That's what Rainer Blatt did. And what you can see here is then essentially starting at around 2003, for the next 2 decades, we continuously pushed to control more and more qubits. And one thing I'd like to emphasize is, one thing is about having qubits, the other thing is about controlling qubits. So you can easily control a large cloud of atoms, a large cloud of ions, but our focus was, please control them, show that you have coherent, essentially what's quantum, can you realize entangled states? And that's why you see here that we already in 2008, that's about 15 years ago now, we realized the first fault-tolerant gate operations, meaning really low error rates, which enable you to go for long algorithms. I then pushed during part of my PhD thesis to control more than 10 qubits, which we subsequently then put into a 19-inch rack, and then we pushed for 24 qubits to be fully entangled, which is one of the things you want to see if you claim to work on a quantum computer. Then I also have to admit my colleagues in the US, that's Honeywell or Continuum, depending on how you prefer to call them, superseded me. So they recently entangled 30 qubits, but I think that's a good thing because it pushes us forward and gives our people an incentive to go on. And as you can see here, in 2018, we decided to found AQT to have more commercial activities there. And a little bit in contrast to Bruno, we don't build everything on our own. Everything we can buy on the market, we just buy on the market. We don't want to be a laser company or build our own electronics. This is something that we can just get off the shelf. So here you see the ion trap. We have a little bit of laser stabilization. We put all of that inside a vacuum chamber, and the vacuum chamber is at room temperature. We don't need any special cooling. You can touch everything, you can look at everything, and everything fits inside a simple 2 19-inch racks. And because there is no special cooling, no nothing, anything else, and the lasers are as efficient as your laser pointers, you can run them for years with just a couple of batteries. The entire system only has a power consumption of about 2 kilowatts, which is similar to the kettle that you need to make your tea. And so also, especially now with the rising power costs, this is something which can be very appealing to say, how can we get more computational power, but without essentially having the operational costs explode? And so here you can see an overview. We've demonstrated a couple of instances in finance, in security, in chemistry, and we are happily looking now more towards hybrid realization together, looking into HPC, working with a quantum computer, because probably this will open up completely new fields. And one thing that's really cool there is one of the different benchmarks for quantum computers is the so-called quantum volume, which is more or less a number for how many qubits can you control with how many gate operations. And we managed to push for a quantum volume of 128, which to our knowledge makes it the best quantum computer in Europe. And we are now looking forward in a collaborative fashion with anyone to push and look into new applications for such a device. And with that, I'd like to thank you for your time and looking forward to the discussion.
Great. Thank you so much, Thomas. Really appreciate that. Okay, third up, we have Chaima Boaza, again, Regional Manager for Middle East for Pascal. So Chaima, can I pass over to you?
Yes, thank you, Laura, the presentation, and thank you so much for the kind invitation. So I cannot relate to the snow because I'm in the Middle East and we have summertime, so I was on the beach not long ago, so sorry for that. I think Hatem can understand very well as well. However, we work with cold atoms, so even if we are in warm temperature, but our qubits, what we use as qubits, are atoms similar to what Thomas was presenting, but we will use different physical phenomena to encode our information. So let me share my slide to give you a quick overview about Pascal and what we are doing. Can you see my screen? Okay.
Yes, you're good.
Yeah, perfect. So Pascal is a company that was established in 2019, and similar to AQ2, it's building on the research and development for decades in the lab. The company was co-founded by Alain Aspect, who got the Nobel Prize last year, and Dr. Antoine Broez, who is a researcher at CNRS, together with our CEO, Georges Olivier Raymond, and with a headquarters in Paris, but we have an international presence today across Europe, North America, and myself, I'm based in the Middle East since 1 year. The company is more than 220 employees today, and similar to the other companies, we are developing the full stack solution from the hardware all the way to applications and cloud access. So I think I don't need to convince you why the interest in quantum is growing more and more, but maybe I can say a few words about our vision, how we see quantum integrating in HPC. So in the past, high-performance computing was mainly focusing on one type of architecture, CPUs. And the past decade, we see more and more of GPUs integrated in high-performance computing centers and these hybrid models. In the future, we think that it will be even more hybrid and integrating different type of architectures and technologies. Quantum is just one of them. You can see it as an accelerator that will come to bring some kind of acceleration or improvement on some specific problems, but the goal is to be integrated within the existing infrastructure and use it as an accelerator. So what we use as qubits, to answer your question, Laura, we use atoms, rubidium atoms that we trap and we manipulate with laser beams. Inside of a vacuum chamber, we can use some optical elements to trap atoms in arrays that are generated by laser beams. So with one single laser beam, we can use this optical system called spatial light modulator to split this beam into very small beams that we call optical tweezer. And in each small tweezer, we can trap one atom and only one at a time. And that will be our qubit. And the two states, the 0 and 1 of the qubits, are the two energy level of the atom. When it is at the very low energy level or the ground state, that will be our 0. And then using a laser to excite it to high energy level, that will be our 1. And by playing on the properties of the laser pulse that we are sending on the atom, we can put it in a superposition and do the control of our qubits. So I think one of the main differences or advantages of this technology with respect to the others is the flexibility, because we are not limited to one geometry. It's not a fixed chip that we build and then we cannot do much about it, because at each new run, we can define a new geometry, load our atoms, move them in space to adapt them to the problem that we can that we are studying. I really believe that today we cannot tell which technology will win or if it will be only one. But I think that each technology has advantages and some limitation. And today we are trying to understand for each technology or for each advantages, what are the best applications? Probably, or I don't know, we will see in the future, but maybe we will have different technologies continuing, and each one will be more adapted to a specific type of application. Again, as the other companies were mentioning, we are working a lot on the industrialization as well. This is a picture of our first generation machine. It's called Fresnel. It's a 100-qubit system. And similar to QT, we use on-the-shelf component, and it has a very low energy consumption. In terms of development of the stack, as I said, we developed a full stack solution from the hardware all the way to applications, and we work closely with end users. Again, because we are in this phase where we need to understand what are the best applications for this technology and where it could be useful. And that will only come from a close collaboration with end users. At the end, we are only scientists and physicists, and we don't know what are the bottlenecks. And by doing co-development, it's the best way to learn, to do benchmark with the best classical solution, and to develop the roadmaps that can fit best the end user goal. Just a final word on the algorithmic side. The hardware is important, but the algorithm and software is same thing. It's as important as the hardware. What are the most efficient way to control this system and to solve the problems? At Pascal, we are trying to focus on these 4 main category or family of problems, and in each family of problems, we develop a set of tools or algorithms to address those problems, and then we can try to adapt those tools to the different problems. So yeah, this is in a brief a look to Pascal and what we are doing, and happy to go further with the discussion later. Thank you.
Perfect. Thank you, Chama. Really great. All right, and then wrapping up before we go into questions and discussions again, and sorry, please excuse me, but I just have to add in these things because I think this is really cool. So adding some extra bling to the conversation now, Matt from Quantum Brilliance, will you give us a little bit of overview of your company and what you're doing?
You're muted.
Oh no, can you hear me now? How embarrassing. There's always one person who starts speaking with a mute button on, and this time it was me. So my name is Mark Mattingly-Scott. I'm here in Stuttgart in Germany, which is reasonably close to the snowstorm hell of Munich, but sufficiently far away that we didn't have it quite as bad, but it's still a lot of snow outside. I'm the Chief Revenue Officer and the Managing Director of Quantum Brilliance here in Germany, and as Laura mentioned, General Manager in Europe. We are an Australian-German full stack company with roughly just over half our team here in Germany and just under half in Australia. Our roots are very much both in Australia and in Germany. The technology of building qubits or building spin systems based in diamond originated here in Germany, was first commercialized in Australia, and so to speak, we're now back to the roots. So our technology is based on building qubits using something called a nitrogen vacancy in diamond. So diamond is basically a crystal lattice of carbon atoms. If you have a nitrogen atom in that crystal lattice, then valency basically mandates that next to that nitrogen atom there is what's called a vacancy, and we can use that vacancy to interact with the nitrogen atom and make a qubit or make qubits. The really nice thing about this technology is that it works at room temperature. It has a few other advantages. I'll talk about those in a second. So what does quantum brilliance do? We don't just build qubits using nitrogen vacancies, but we're also in the business of preparing what are called functional materials. So you can make qubits with nitrogen vacancies in diamond, but you can also make sensors, and that is an increasingly interesting and commercially relevant area in the deep tech industry. And the diamonds we use for making qubits are also very, very interesting and usable by sensing companies. We also then take our own diamonds and put qubits on them, initially or currently for evaluation and for integration purposes. But then we're also very much aware of the fact that if you have a truly room temperature quantum computer, how can you find use cases where the very low size, weight, and power can be exploited? And to explore that, we're looking at customer integration applications. This is a photograph of our first machine. The silver box, this is a photograph from the back. The silver box in this picture was taken at the Pawsey Supercompute Centre in Perth in West Australia. It contains 2 qubits, and essentially it was used, or is being used, to evaluate how to integrate quantum computers and quantum algorithms into classical HPC workflows, and also to understand about deployment in what is actually, and I probably don't need to tell anybody here on this call, quite an aggressive environment, especially acoustically, which causes or presents a lot of challenges to almost all other quantum computing technologies. Fortunately, diamond is resilient to that. What is our North Star? So the key technological innovation that we are working on is achieving a deterministic, or implementing a deterministic way to create these qubits in diamond, and to do that at industrial scale. That's our North Star. And what does that North Star look like? It looks like a world in which you have CPUs, GPUs, FPGAs, and QPUs, all of the same sort of size, the same weight, the same dimensions, and particularly the same power consumption. The machine I showed you on the previous foil consumes about 180 watts. We expect that to go down significantly. And in principle, the entire control electronics is something you would find if you opened up a 4G or a 5G telecom base station. So fairly simple optics, incoherent photons, some simple RF, and some simple microwaves. The key technological challenge is in making large number of qubits as I said, in a deterministic way. That's core IP that we own, and we're here in Germany, among other things, to develop that IP, and here in Europe to industrialize and make diamond the material that enables the quantum computing or the qubit revolution to actually happen. Thank you for your attention on that, and I'll hand you back to Laura.
Great, thanks, Mark. So one thing I want to ask from each of you, and you know, Chima, you mentioned this, and some of we touched on this topic. I think one thing that was interesting, or was a new information to my team of HPC specialists when they came into this field of HPC QC integration. One of the surprising things, there are different types of qubits. So a qubit is not a qubit is not a qubit, right? These are all a bit different. So just to kind of baseline, what is the difference between your qubits?
This is a question to me, or
this is a question to all of you, but since you started, Chima, yes, we'll start with you.
I can start. So a qubit is simply a description, mathematical description, a state that respects the laws of quantum physics and can be in 0 and 1, superposition, entangled, etc. So talking about a qubit is just something mathematical, but on reality, from practical point of view, how can we make qubits? We have different options. We have different physical systems that we can use. And that's what we mean about different quantum technologies. It means what physical system that we are using to encode and process the information. So there is the atoms, the diamonds or the vacancy, the superconducting loops, the ions, the photons, etc., etc. All these are physical systems that can be described by quantum physics, and their behavior can be described by quantum physics, but they don't behave the same. We don't control them in the same way. So in our case, as I said, the two state of the atom, the 0 and 1, corresponds to two energy level of a qubit. The two state of the qubit corresponds to two energy level of the atom. For another technology, the 0 and 1 will correspond to something different. So then the question is, what is the best physical system that we can control in an efficient way and can be protected, but in the same way we can access easily? And that's a difficult question to answer, because at each time you will have some good points, either the flexibility or the ease at which you can build your qubit, or how good you can interact with it. But from the other side, you are losing something. You are losing on the quality of the qubit, or how long you can interact with it, and etc. So it's a balance that we need to find. And that's the main development and research happening today for each of these technologies, how we can improve on all those aspects. But at the end, saying a qubit is just conceptual something.
Okay, great, thanks. Anyone else want to answer that?
I just want to say this was pretty good.
That was a great answer.
This was a fantastic explanation.
Very good. Okay, so but kind of going to that, I mean, we come from the realm of CPUs and GPUs and FPGAs and IPUs, all these different sorts, and they all have a different sort of computational behavior to them. Is there a way to describe, I mean, what sort of behavior do you notice? What is it good for, sort of QPU style computation?
I can continue if no one anyone else wants to. Okay, I can continue. So again, this is a research field. What can it be used for, and something that is really useful for the end users? So if we look from purely scientific point of view and a research point of view, we know that these technologies are useful for research itself. And this is the idea of doing quantum simulation. And here, when I talk about quantum simulation, is not simulating the behavior of a quantum computer on a classical computer. Here, I'm talking about simulating the behavior of a complex quantum system on another quantum system that we understand very well. And using these kind of systems, especially I'm coming from the cold atom field, so using those systems that we can control very well, their interaction, etc., to study some material science or condensed matter complex problems, we know it's very useful for that. And it has been the case for a long time now in the lab. It's not something new to use quantum systems to study other quantum complex systems. Now, the challenge that we are facing in the community is how to go from the lab to something that is useful on an industrial level. How can those machines could be used for a real problem in industry, in the energy sector, in the automotive sector, in pharma, in whatever you call it. So here we started identifying, let's say, some classes of problems where there are maybe a potential, because today there is no application that has a clear quantum advantage. But we have like some hints, some expectation, and here we are maybe looking to some optimization problem, complex optimization, combinatorial optimization problems, some tasks of machine learning like classification or regression, maybe on the chemistry side, quantum chemistry simulation. But we are still testing and learning. So I don't know if this answers your question.
Okay, so I want to bridge off of a point that you just said. So you mentioned the term quantum advantage. So I mean, one term that we've heard a lot, I think appropriately it's dying down is quantum supremacy. Now we're talking about quantum advantage. But is quantum advantage really about just outperforming a supercomputer, about beating a supercomputer? Is that really what this is about, or what other advantages are there for using quantum sorts of quantum computation style and quantum systems? So maybe Bruno, this may be something for you.
Well, I like to keep with how the term was originally intended. It is about outperforming not just supercomputers, but the best algorithm to solve a given problem in the best machine available or existing. That is a definition I think is a very good one. What we can discuss is, what does it mean outperform? It might mean that I can get to solve a problem that's larger than I could before. It might mean I get to solve a problem with less energy, and then I don't necessarily need to compare with the largest supercomputer available. I can perhaps compare to a smaller subset. It might mean I can go and get a more precise answer for that problem. So with my resources now, I can not only shrink the time, but I can also go in to have more precision. Those are all things that are very valid advantages. And I particularly think the energy argument is a very good one that's speaking a lot of base. But it has to be about outperforming in some way the best algorithm to solve that problem in all the machines that we have.
Okay, Thomas, Mark?
Yeah, I just wanted to add something to what Chana said. I think if you look at an HPC system, you have racks full of disk drives or SSDs, you have racks full of memory, you have CPUs, and you have GPUs, you may even have some TPUs. The CPU is very good at a very specific task, which is steering things and controlling things. The GPU is very good if you want to do anything with matrices. Any operation, any mathematical problem where you can formulate that as some kind of matrix operation is probably going to go fast on a GPU. If you can formulate something as a tensor operation, it's probably going to go fast on a TPU. The question then is, okay, so what's going to go fast on a QPU? And the simplest answer is anything that can be represented by a complex probability distribution. The problem then is, how do you translate real-world problems into that formulation? That's an entirely different task. And that's where this issue of what's quantum supremacy, what's quantum advantage, what's quantum utility. IBM is even using this term. And that relates to, where does the quantum computer, or where do the qubits, in the context where they're being used, outperform the classical alternative? And outperform could mean, as Bruno said, it could be faster, it could be more accurate, or it can consume less energy, or ideally two or even all of the three of those. If you imagine you have some small device somewhere which consumes a couple of 100 watts, and it's able to solve a problem, but you can bring in a quantum computer, and for 100 watts of energy, you can solve the same problem in half the speed and at 10 times the accuracy. Then you've got quantum utility. They've got something that's actually got an economic value. And that's where the whole industry is heading, I think. It's less away from the huge, industrial complex size quantum computer, which maybe, maybe there's, I think as Shaima said, I'll have to stop speaking a mixture of German and English, excuse me. As Shaima said, there will probably be use cases and applications where all these different technologies have advantages and will be used. Who knows? I mean, if you look at the silicon industry, which started back in the 60s, we still have other semiconductors in use for very particular niche markets. But I think the main race that's going to be run will be around finding that very first economic benefit where quantum computing can actually provide some benefit in problems specifically which can be expressed as complex probability distributions.
Okay. Great. Shaima, you wanted to an add-on point?
Yeah, may I add maybe something on this energy aspect, because this is very important. I'm currently at the COP28 in Dubai, and I can assure you that the question of data centers going green is really, really big topic here. Because yeah, even if we talk more about the oil and gas and all those polluters, but data centers, they consume more than 2.5% of the total energy globally. So with the increase in AI and all the digitalization and all those targets, the energy consumption of data centers will grow even more and more. And if there is a possibility to reduce it by replacing some of the tasks using a quantum computer that consumes less, then there is definitely an advantage.
Mm-hmm. Okay, so a question then. So we're talking about all these advantages of quantum computers. Just the elephant in the room, are quantum computers going to replace supercomputers and HPC systems? Thomas, I see you shaking your head violently.
It feels that we often talk about quantum computers as if everything has been solved. Whereas it feels like when I talk, probably it's the same experience for Bruno and Shaima and Mark. It's like, to a large degree, we control quantum computers essentially in assembler language in little scripts. And we like a couple of months ago, we were attending a quantum software engineering workshop, and the computer scientists were complaining that we only have scripts. We don't have an object-oriented language. We don't have libraries which are quantum enhanced and really make use of the hardware to their utmost, and so on and so forth. And what they actually wanted to have is like, can we have a library which magically like understands there is a quantum computer in the infrastructure, and you know what the quantum computer can actually do, and then decides on its own which tasks shall it offload to the QPU, and which ones does it maybe want to keep on the classical processor. And I think like this how to say, training and knowledge of the system of a very heterogeneous infrastructure, where you say I have a CPU, a GPU, an IPU, a QPU, like that knowledge on you give a certain problem, you throw a problem into the room, or you're like into your HPC system, and it can decide, given the structure of the problem, given the resources available of the different devices, which one is the best system to operate it on. This is something where I think we quantum people don't have to reinvent the wheel, but rather work together with the HPC people to build and leverage existing knowledge and structures to more quickly demonstrate these ideally economic benefits of a quantum processor. And when that's a little bit of, let's say, an Austrian approach, rather than competing with HPC, I'd rather collaborate with HPC.
Very good. Any other points there?
I think Mark already gave the breaking down of it, right? Thomas is absolutely right. Also with how the experience of talking to several people, even in the community. But the point is that all of these different processing units, they have their own purpose, and they have to work together, eventually in a way that the user doesn't even need to know. But they have to work together to solve the problems. And quantum is one of those specialized processing units that can help, well, we'll get there, that can help us solve problems, specific problems that will have to be formulated in a specific way. And all of those things together, they will be understood eventually as HPC. Today we think of HPC plus quantum, and that's not the right approach. HPC and then there's quantum here in the middle.
So I'm the moderator, so I shouldn't be injecting a whole bit here, but I do want to inject this one point. I am firmly of the belief that quantum computing is high performance computing. At the end of this day, all of this is about achieving a new level of performance for really groundbreaking results. So I definitely agree that I see the term HPC morphing as we move over time as well. Okay, so that's all great. So I mean, we have these really interesting QPUs. We've got quantum mechanic effects happening, mathematical models, all of this. We've got the CPUs, the GPUs. Hardware is fantastic, but at the end of the day, what makes it all go is the software, right? So you know, kind of with that in mind, with this unique QPU, what kind of challenges are we facing to merge QPUs in kind of an accelerator sort of capability within this larger HPC ecosystem? But what are we up against?
Well, maybe I'll just start off. Honestly, I don't think we know it. We don't know what we need to do. And even if we look at the screen, you have 4 different vendors of quantum hardware, and our interfaces to our users are not the same. And obviously, if we want to then deploy our systems to HPC, to LRZ doesn't want to go and say, oh, okay, do I have to now do the work to interface this to your system? And then each time I get a new system, I have to do this again. So even those basic things, we don't know yet how to do. So if you go across making it more difficult, how do you actually allocate resources? How do you actually make sure that you use this expensive quantum computer as much as possible? You cannot follow just your standard way of resource allocation that one typically does on HPC. You have to think of a new solution. And in that, the quantum vendors, we can only contribute to the discussion in the sense of educating the computer science community, the HPC community, on quantum capabilities. But the solution, you guys have been doing that for ages. So the solution lies, well, we rely on you to actually come up with that.
Mm-hmm.
I think it needs both sides. So in the software engineering workshop, the cool thing was that we probably spent half of the time just finding the same language, because it was fun. It's like, for instance, we talked about how would you verify that the device does what it should do. And they were used to, I just run a classical circuit up to a point, stop, check, is it giving me the right result? And then they went on. And they were complaining that a quantum computer is like, the very moment they stop and measure, it destroys the information. And let's say innocently, they asked us, can't we make this randomness go away? And we're like, no, this randomness, that's when the power is hidden. And so we spent some time talking, and in the end it was like, yeah, okay, then we just have to find new ways of how to verify that code, also like just on the software development part, that everything is working. But that's I mean, that's the cool thing and interesting phase now, where you'd say you bring in a quantum person, you bring in a control person, like electronics and so on, you bring in a computer scientist, all of them in the same room. And after some, let's say, polite misunderstanding for some time, ideally, you then have a synergy to create something notably larger than the individual knowledge was before. But that takes time.
Yeah, Chema?
Yeah, I totally agree with Bruno and Thomas on this, and I think the best way to move forward is by really working on concrete projects. And this is one example that integrating an AQT machine with an LRZ. In our case, we are working on this European project HPCQS to install 2 machines at Gency in France, and so the TGCC in France and Jülich in Germany, and IQM is working with HPC centers, etc. So the only way, because we can discuss, and there are a lot of conferences to debate and brainstorm, etc. But the best way to do it is by working on concrete projects. And I think here the European projects are very, very valuable. And then the European Commission has a key role to play in bringing those words closer together and force them kind of through those projects to collaborate and to define those models and common frameworks to work with. If we just continue evolving each one in its own word and bubble, that will never happen with all the good willness in the world. The best way is to work on concrete projects. I think in Europe, it's really a good development that we are seeing with a joint undertaking with different initiatives, with ATP for HPC that integrated a quantum workshop as well. So we need more of those kind of projects.
Mm-hmm. Great. Great, that's a really good point. So I want to go back to a point that Thomas was talking about sitting in a room with different communities and kind of the, a little bit of the crosstalk and ships passing in the night in terms of terminologies. So simulation in physics does not equal simulation in HPC. There's these different definitions and whatnot. So just, for the people who are in the HPC space and they're interested in this is their interest is piqued. What would an HPC person need to do to come into this HPC QC space? I think a lot of people see quantum and just get turned off or go, oh my goodness, no. How hard is it to come into this mid space of quantum HPC as an HPC person?
I would claim there is no barrier at all, because we are desperately looking for those people who are willing to put a toe in this unknown water. So it's like, I can tell you, whether it's academic or industry in Innsbruck, as like in Austria, there are a couple of professorships which are announced where they desperately look for computer scientists who are willing to do a little bit, or at least have some quantum interest. You don't even have to have started yet, just do it. And on the industry side, it's the same. So if someone is interested, I'm very much convinced that they can reach out to Jaima, to Bruno, to Mark, to me. And all of us would say, yeah, if you have some interest and good ideas, we'll happily spend time on you to bring you together with the right people, depending on where your interests are on every corner, on every continent.
Yeah, I was going to say, raise your hand if you are hiring people. If you're looking for people, yeah, okay, that's what I thought. Exactly, we all are. So there's no shortage. So I mean, this is really just a call to action. Honestly, and again, I don't want to interject because I'm supposed to be the moderator here, but I've got this amazing team, and what we're really seeing is that if you're an HPC person, there are so many interesting corner cases for integrating quantum in, the type of scheduling that you do from the HPC to the quantum, the interfaces that you have to think about. If you think you're a top gun and you're pretty good at what you do in HPC, try integrating quantum into this, and it really kind of ups your game and ups the challenge, and it's really some interesting problems that you can work with. Okay, I just kind of because we're getting towards the end here. So one question I wanted to throw out to all of you. So when you're out in the community and when you're speaking with different groups, what's a question that you are frequently asked about quantum computing from non-physicists, educated laypersons, maybe coming from other fields but not physics? What's kind of a question that you frequently get asked?
I can start if you want. A wide range of questions depending on the interest of the person and in which field they work. But maybe the first question is, what can I use it for? What it will be useful for, especially in my industry, in my vertical. This is for the end users. For more curious people, when we will have the fault tolerant quantum computer, and when are you breaking all our encryption? And the third question is, how can we start? Really, how can we start learning, and how can we are interested in quantum, but we don't know how to start. So those are the main questions that I get.
Great. Anyone else?
Yeah, I would say the question I get asked the most is how do qubits work? It's either surprisingly easy or surprisingly difficult to explain that. The second question is, when will we see a real use case? When will we see some real economic benefit? And nobody can give you an answer to that at the moment. But I think the challenge there, or the answer there, is to try and relate quantum computing back to real world problems and real world economic and performance benefit. So when I explain about quantum utility or these kind of things, then I often see a light bulb go on and people realize, okay, so it's a technology which is, or it's a set of technologies. The four of us here represent a cross section of that. It's a set of technologies which holds immense promise. The exact path to realizing that promise is still open, still not defined. But I think if you focus on what the outcome is, or what the expected outcome is, and then assess and understand those technologies in that context, then that's by far the best strategy.
Great. Anyone else?
So I one question that I really liked, because it was for me highlighting how hard it is to explain where quantum computing can go, was once we had a person visit us, look at the device, and he asked us then, so how many laptops is that? And we noticed then it's like, well, but how would you evaluate like one computer versus the other? Is it the clock speed? Is it the size of the hard disk? Is it how many processes you can run in parallel? Yes, no. Is it the size of your screen? And so we said, like, this, it's first of all, like, there will be not a direct comparison, because you first have to clarify what do you care about? Is it the power consumption? And that brings me back to Bruno and Jaima and Mark. It's like, depending on what your requirements and goals are, and therefore your measure of metric, what you care about, power consumption, speed, clock speed, number of steps it takes until you get the results. So is it time? Different devices will have different use cases, and it also highlighted then to a large degree that we will likely talk about special purpose devices. So it will be good for one thing, might not be good for something else. And so even such a simple question like how many laptops is it, was then starting to have, then we had a really good discussion with that person, because like the person couldn't answer it himself when we would say, like, please compare to computers. Is it mobile? Like, probably Mark's devices can more easily be mobile compared to some of our other approaches. Do you care about that? Yes or no? And so I think there will be not one winner takes it all, because also on the classical side, we don't have that. As you said, Laura, we have CPUs, GPUs, QPUs, and so on, depending on what your requirements are. But that's something I think which is important also to communicate, because it feels to me that people were saying, like, which one will be the winning approach? It's like, for which use case?
That's great. One thing, so I mean, Thomas, you mentioned this about about scaling, and it just hit a nerve with me because we've crossed into now this exascale era, right? So now we're computing at exaflop range. And I'm just kind of curious, what does the evolution, what does the future of the QPUs look like? I mean, is it just about getting more qubits and having them more stable, connecting more with each other? Is it just a scalability of the qubit count and the stability, or are there other factors, engineering factors involved? What does the progress of quantum look like, of these QPUs?
Well, maybe I'll go first on this. This is you already mentioned what people typically know: number of qubits and their quality. Once those things scale, then we can have fault-tolerant machines. We can correct for errors, which is one of the big problems we have with quantum computers. But then there is the practical side of it, which is often, well, all of us here in this call, we know it, but most people don't realize that it's quite difficult to actually make those, well, turn those labs into a product that you can deploy somewhere and that's going to be stable, low maintenance, low cost. If the prices continue, if we just scale prices that we have now to millions of qubits, no one can afford those systems. So prices have to come significantly down. The space that it occupies has to come significantly down, and so on and so on. Some of our technologies are better suited for some of those things. Some are better suited for other things, as was already mentioned today. But those are really important engineering challenges. And we are certainly all working on that, but we are all also certainly needing to take significant steps still.
There's a ways to go. Anyone else on that question? Okay, well, sorry, go ahead.
I think it's like you could say, what's the goal? It's like, I mean, I don't like the question, but it's like someone would say, where does this quantum advantage potentially kick in? But one thing you could do is you could say, where is the limit for classical devices? And it's roughly somewhere around 50, 60, 70 qubits. So it's like the very moment we can control 50, 60, 70 qubits with really, really high fidelities, that needs to be added. And ideally fully connected and whatnot. So there are many little details, but that's what we need to aim for. And so you could say, I might not need directly 1 million qubits. It's like maybe it's better to aim for something that Chima has, where she says I can have 100, 200 atoms, and all I need to do now, and that sounds simple, is improve the control. And Bruno probably also is like, he is similarly working towards 50 and 100 qubits in the next years. You could say, how do I then get not so much notably more qubits, but a higher level of control? Because at the end of the day, I can generate, and no one is present, but it's like I can generate millions of photonic qubits, just the control really sucks by switching on the light. This is like having lots of noise is not something anyone wants. It's like it's the control which is the engineering and the hard part. But that also means, which I find cool, is it's like it's not years away. It's like this range of controlling about 100 qubits, whether it's now superconducting NV, atoms, ions. It's not too far away. And then it will be a battle of how to control, reduce the error rates to a point that we can do something meaningful. And I think that's maybe one for me, it's always like good that it doesn't feel like 20 years away. This 50 to 100 qubits, it's actually at the level of where we are almost comfortable at being a number of qubits. And yes, we might add some redundancy for error correction and so on. But again, it's not a factor of 1,000, but we talk about a factor of 10 or so on top. And so it's not too far away. But again, it's like, I think Mark mentioned it. No one wants to answer this question about how many months is it away.
Well, I mean, so to that point, and to kind of wrap up, I mean, so LRZ, so St. Nicolaus has given LRZ our Christmas present, right? It's being unloaded right now as we speak, as I mentioned at the beginning of this. So what is your Santa Claus wish list? What would you like to have for quantum systems if you got your wish list this year? Mark?
Well, I'd like to have a QDK in LRZ as well.
Okay. Fair enough. Anyone else?
It's not easy to have only one wish, but I think at this stage, I would like to see as many machines available as possible, and really available in a large scale to the public, to the students, to the researcher. And that's the only way we can improve and develop, by testing and building real project and run it on real hardware and learning from that. Again, it's we are physicists and scientists. We know about quantum, but we don't know about all the challenges that could be faced. And the best way to learn is to work on concrete projects. So by making those machines as available as possible and democratize the access, that will be the best for the community in general.
That's a great answer. Yeah. Bruno, Thomas, any Christmas wishes?
I'd be more on the let me be the bad one, the Krampus from the mountains, and Bruno can be the final good one. I would be actually the one, putting the Krampus into the room to say maybe there should be a couple of more entities that help to separate hype from reality, because there are people promising the world just to be seen and attract maybe money where it might not necessarily need to go. Let's put it that way. Because it's like it will not serve world hunger in the next 2 years. We will not likely have personally targeted medicine in the next few years. There maybe if there would be just a little bit more communication, it's like is whatever Bruno is saying realistic, yes or no? And with some entities, I would say, if Bruno said so, then it's probably correct. With some other entities, I would be more careful. And there are a couple of, what's the English word for Trittbrettfahrer? Which maybe overpromise, and it's the community is also at risk of suffering, like at the risk of losing credibility for the years to come, because it's more like a marathon and not a sprint. And we are, with some of the activities going on, we are more hurting ourselves than actually pushing the field forward. And with that, the Krampus is staying silent now.
Oh, that's a really great point. Okay, so Bruno, we're relying on you to end it up on a cheery note.
I'm gonna be somewhere in the middle there, because I actually wanted to touch on what Thomas was saying, but let me try to formulate it in a different way. I think what I would like to see for my St. Nicolaus is that the community finds a more cohesive way of talking about the promises of quantum computing and the timelines associated to the different parts of it. And the media does its part as well, because unfortunately, I do think that part of the hype doesn't come from the community, but comes from those putting our word out, which is very important. But then often I read articles that I cannot agree with. And I think this is something really important at the same time as keeping everyone's attention to the fact that when this technology is available, it is going to be game-changing. All signs point to that. The four of us are dedicating our careers to that. it is going to be game changing. So we need to keep investment coming. So hype down, but look into the horizon and continue putting the money in.
For the sustainability, very, very good point. So that is a very solid point, I think, to wrap up our session on. So thank you, the four of you, very much. Coming from the HPC perspective, I hope that the viewers have gotten a little bit more insight into this emerging technology and how it could be beneficially brought in to the HPC ecosystem and truly become another facet of supercomputing, and how we might be able to slowly start down that pathway to apply it to some of the problems that we currently have, that we haven't been able to get further with, or that we have new ways of discovering new innovative results from. There's a lot of potential here, and it's a really exciting time, I think, in the HPC space, with AI gaining maturity here over time. Still a long way to go on that spectrum as well, but that's getting a bit further down the road. Now we've got quantum coming in. I mean, just in terms of heterogeneous compute and all the different possibilities that are around, it just seems that we're really ripe in the years to come for some really interesting computational solutions and some really interesting results that stem from them. So thank you very much to our four panelists. Really great comments and thoughts, and all the best to all of you for a very lovely remainder of the St. Nicolaus Day. And for those of you that engage in the holidays, or passively observe it, or just enjoy the spirit of the holidays, may you have peace and prosperity, and may all good things come to you. And hopefully we will see some really great results coming from you in the HPC space, and maybe even applying quantum to it. So with that, Hatem, I will turn it back over to you.
Thank you so much, everyone. You guys provided actually a great gift for our HPC community with this panel-style webinar. We appreciate your time and your effort in putting it all together. Really enjoyed all the honesty here, during this exchange with all of you. And I'm sure our community will be welcoming this content and looking forward for more collaboration. Thank you so much.